So we'll continue with the second half of 8.3, center of mass. We'll start by defining a few terms, and we'll spend um, a, a decent amount of time just talking about non-calculus examples before we get into the calculus here. Okay, so to begin center of mass, we're going to start by defining the word moment. Moment is the tendency to produce rotation. You may have heard of the word torque. Uh, they mean the same thing. A moment or torque. Um, how much potential or tendency do you have to produce some kind of rotation? So you really hear torque as it applies more to like automotive or some kind of like engines and things like that. How much torque does this motor produce, right? How much rotation, how many revolutions per minute, is it capable of at any given in any different circumstance, right? So moment, same thing. Um, okay, tendency to produce. So we're thinking of things spinning. Let's just kind of start with that. Okay, so we'll go to a one-dimensional case. One-dimensional, so just imagine a straight line, and we're going to place masses at different locations on this line. Everything is sort of like focused on the origin. Okay, so as we place these masses at different locations, think of it as, is that going to produce rotation about the origin? So, imagine it's like, bolted in place there at the origin, and this thing might spin either to the left or to the right. So in this case, I just drew um, a few masses here. So let's say we have mass 1 located here at x1, mass 2 at x2, and mass 3 back here at x3. And so you can imagine, well, the mass, the size of the mass matters, and also how far away it is from the origin. And then things on the right versus things on the left will tend to balance each other out. So now how would we go about calculating the moment in this one-dimensional case? So we'd call it the moment about the origin. We'd call that m sub o, moment about the origin, and you kind of see, we take the sum of the products of the masses and their distances. So m1 times x1 plus m2 times x2 plus m3 times x3. And you might think, well, wait a second, what if some are on the other side? Well, then x3 would be negative, and so that negative x3 would balance out maybe some of these other ones, or maybe, go beyond what these other ones are adding up to. But okay, the sum of all of those masses times their distance would tell you how this thing might spin about the origin. So let's talk about what results we might get. If the moment about the origin equals 0, perfectly 0, then the things on the right are perfectly balancing out the things on the left, and we have equilibrium. There's no rotation at all. However, if we get a positive result for our moment about the origin, that means the masses here combined with their distances are too much for what's on the left, and it's going to rotate. We say to the right, but it's kind of like, to the right if you're thinking up above, so it's kind of coming down this way. If that moment about the origin is negative, then this one wins, if you will, and it's spinning back to the left, going that way. Okay. So what would be the center of mass? Kind of rise this up. The center of mass, we would say, is the moment divided by the total mass. So it's almost like there's almost kind of an average happening here, although it's not quite that, but it's kind of got that feel. So take your moment about the origin and divide it by the total amount of mass in the system. So we call it m, but in this case it would be m would equal m1 plus m2 plus m3. And that coordinate would tell you where on the x-axis the center of mass is located. So if the center of mass is located right at the origin, well, then it doesn't spin. But if the center of mass is a little bit positive, then it's going to tend to rotate to the right. Or if this center of mass is a little bit negative, it'll tend to rotate left. Okay, and that fits, our description of the moment. Okay. We'll do it for the one-dimensional case. Let's move to the two-dimensional case. By the way, you will see the one-dimensional and two-dimensional in the homework, along with the calculus style. In the two-dimensional case, all right, now we have an x and a y-axis. So let's imagine M1 is located maybe here at x1, y1. M2 I placed back here. Let's say that's at x2, y2. And maybe M3 is down here. That's x3, y3. How are we going to go about calculating a moment in this case? Well, it turns out there's actually two moments. We think of the moment about the y-axis and the moment about the x-axis. So we'll get some kind of rotation horizontally, and we might have some kind of rotation vertically. So let's talk about each one of those. Let's start with the moment about the y-axis. So the moment about the y-axis, it's the y-axis, but this is horizontal rotation. We call it m sub y because it's the y-axis. However, it involves the x values. And actually, let me just go ahead and simplify this to match my drawing there. Okay, so the moment about the y-axis, that's horizontal rotation. So that's going to be really the same thing that we just saw with the one-dimensional case, m1 x1 plus m2 x2 plus m3 x3. We only care about the x values if we're thinking horizontal rotation. And so kind of here's the depiction. Like, it doesn't matter where they are located vertically. It's all about just those x distances. How is it going to spin this way? All right. We will also have, kind of updating my lecture as I'm teaching. We'll also have a moment about the x-axis, but well, it's the x-axis and we call it mx, but this is actually vertical rotation, so it involves the y's, and well, same idea, m1 y1 plus m2 y2 plus m3 y3. Now all we care about is those vertical distances. How far are you away from the x-axis? That would cause the vertical rotation. And in this case, you can see that y2 would be 0. And so actually y2, if y2 is 0, that doesn't play any effect in the rotation this way. It would all come down to m1 here and m2 there and their distances. Okay. Once you have those moments figured out, those values, then how do you get the center of mass? Okay, so we're going to call the center of mass the ordered pair x bar, y bar, where x bar is my over m. Again, it's like, this seems to be backwards. X bar uses my, but that's because we're thinking it's horizontal rotation. And y bar uses mx because mx talks about vertical rotation. And again, m, well, that's the total mass in the entire system. So it's pretty cool once you get that ordered pair, and you know where that ordered pair is located, so you kind of go back to your drawing and, maybe here, let's imagine all of these masses are the same. It's just a matter of the distances. Maybe this center of mass would be like somewhere in there, if all the masses are the same. Very loud truck driving by. I'll just pause for a moment. And so, even though there's nothing located here, it's still, things are like revolving as if all of the mass was in that one spot, is kind of the way it works. Okay. So, let's look at, again, this is a non-calculus example. Looks like I'm just showing you everything before we get to the integrals. So you can see that I've erased and changed this quite a lot, and trying to be as strategic as I can. So I've drawn an XY plane, and you see all of these little tick marks. So that will tell you where these are located, and the number next to it is the mass. So let's say we've got a mass of 5 located right there, a mass of 10 located here, and a mass of 2 located down here. If we were to find the center of mass, we'd say, okay, maybe we start with my, that's the horizontal rotation. So we'd take 5 multiplied by its x-coordinate 4, plus 10 times its x-coordinate -1, plus 2 times its x-coordinate -2. Put all that together and you would have 6. Then we'll find mx, the moment about the x-axis, that's the vertical rotation. So we'll take the mass and multiply by its y value, so 5 times 0, plus 10 times +1, plus 2 times -5. And it just so happens to turn out, put all that together, and you get 0. So there's actually 0 vertical rotation. It's only horizontal rotation. So then if you wanted to find x bar and y bar, you would take your respective moments. So x bar uses my. And where does that 17? What is that 17? That's the total mass, 5, 10, and 2. And y bar, well, that's mx over the same number, 17. So we can see the center of mass is 6 over 17 comma 0. And where would that be? So, okay, we're right on the x-axis. 6 over 17, well, that's just a little bit off of the origin, right? So this center of mass, you'd expect it to be very close to the 10. It's just a little bit right there. So it's just got a tiny bit of rotation going this direction. Okay. I think we're going to stop this video here. We'll do the calculus in a moment.